Welcome to the revision of Bachelor of IT, Computer Systems IT1205. Today we are going to talk about data representation and arithmetic 1. So let's start with the rundown. Today we are going to talk about binary to decimal, decimal to binary, hexadecimal to binary, binary to hexadecimal, and representing numbers using 2's complement. So this is the section you will be getting 3 to 5 questions in your question paper. So let's start with the first title, binary to decimal. So as you can see in the decimal system alphabet, it has 10 separate digits start from 0 to 9. And the binary system alphabet, you can see there are only 2 separate digits, which is 0 and 1. So in general, the position value is really important when you are going to deal with binary numbering system. So basically the positions values in a binary system are the power of 2. As you can see, the first position value is 2 to the power 0, which means the decimal value is 1. And the second position is 2 to the power 1, the decimal value is 2. And the third position value is 2 to the power 2 and the decimal value is 4. So likewise. Then here you can see in the first position, as I mentioned, that 2 to the power 0 equals to decimal value 1 and 2 to the power 1 equals to 2. So likewise you can see we have used 10 bits here, which is 1 byte, and you can see the 8th bit is 2 to the power 7, which means the decimal value is 128. So basically when you are converting any decimal number to binary or binary to decimal number, you have to consider this position value. So as you can see, let's take the example 1. You can see here 1 0 1 1 1 1 0 and 1. So if we are going to convert this binary number into the decimal, we have to consider the position value. As you can see, there is a 1 in the 8th bit, which is 2 to the power 7, the decimal value is 128. So we take it, the decimal value 128. Then we can see the bit point, the binary value for the 2 to the power 6 is 0. It means we do not want to consider this 0. Then there is a 1 in 32 position, we take it here. There is a 1 in 16 position, we take it here. And there is a 1 for 8, there is a 1 for 4, there is no 2's, the binary value is 0, we do not consider this, and there is 1 for the position 1. So you can take the 1 here. Then you can take the sum of these numbers and you will end up with 189, which is the decimal value of this particular binary value. So at the same time, you can see the example 2, 0 1 1 0 1 1 1 0. Here you can see there is a 1 for 64, so we take it here. There is a 1 for 32, we take it here. And there is 1 for 16, there is 1 for 2 and 1 for 4 as well. So we all together we can see the sum of these numbers is 118. So this is the decimal value of this particular binary. So likewise you can convert one binary to decimal. So you have to consider about the position value. So how you are going to convert the other way around, decimal to binary? So it is really important. You can come up with 2 different methods. So first one is dividing method. So let's take an example and explain. So first you have to do the divide the decimal number by 2 until you get 0, while indicating the remainders in each step, and write the remainders bottom to top from left to right. For an instance, let's take this example. So we want to convert 57 base 10, which means decimal, to binary. So we divide 57 by 2. You can see 57 divided by 2 is 28, with the remainder is 1. Then we divide 28 again by 2, then 14, we have no any remainder, which means 0. So likewise we divide the number until we get 0, and each step we can write down the remainder. Then you can see in the last step there is 1 divided by 2 is 0 and the remainder is 1. Then what we have to do is we have to take this remainder from bottom to top and write it down left to right. 1 1 1 0 0 1 1 1 1 0 0 1. So you can double check your answer with position values. You can see this one for 1, 2, 4, we do not consider 2 or 4 because the binary value is 0. Then the 8, 16 and 32, which means 32 plus 16 plus 8 plus 1 equals 57. So there is another example. Convert 100 to the base 10, which implies that 100 is in decimal, to binary. Then we again do the same steps and we divided 100 by 2. Then you can see the remainders. Again you write it from bottom to top, from left to right. 1 1 0 0 1 0 0, power is 2. Again you can double check your answer with position value. This is 4, this is 32 and this is 64, which means altogether you will get 100. So this is how you are going to convert binary to decimal and decimal to binary. So there is another way to convert decimal to binary rather than dividing by 2, which means simply you can consider about the position values. As you can see, this is the 57 and this is the position values we have used. So we can simply put binaries ones to relevant numbers. For an example, if this is 57, can we hold any 64 or 128 for 57? No, we can't. Therefore, we can have 32 inside 57, so we put 1 here. So you can see there is another 25 remaining. So can we have another 16 here? Then 25 minus 16 is 11. Again you can see likewise you can fill these things and come up with how you can add each number and get the 57. So here you can see 32, 16, 8, 2 and 1. Again here 100. You can see there is 64 and when you put 1 it considered as 64. When you put 1 here it considered as 32, which means you have here 96. We only need another 4, which means we can put 0, 0 and 1 for the 4 value, which means the third bit position, and other 2 bit positions are zeros. Then likewise the use in the subtraction method also you can convert any decimal to binary. So let's come to the next topic, hexadecimal to binary. Hexadecimal is another numbering system which consists of 16 separate digits which start from 0 to F. You may wonder what are the A, B, C, D, E and F. Actually those are the numbers representing in the hexadecimal numbering system. So A stand for number 10, B for number 11, C for number 12, D for number 13, E for number 14 and F for number 15. Okay, let's see. Now you can see since we have 16 different symbols or 16 different digits, at least we need 4 binary positions to represent one of these numbers. It means if we have 4 binary digits, we can have 16 different combinations of ones and zeros. For an example, 0 0 0 0, 0 0 1 0, 0 0 1 1, or likewise we can have 16 different symbols or the 16 different digits or the combinations using 4 binary digits. Here you can see now what we do is we convert these 16 digits into binary patterns. You know, since this is the hexadecimal, So each one of these numbers can be represented by 4 binary digits. So you can see some examples. 0000. So in hexadecimal it is 0. When we consider the binary position value, this is 1, 2, 4 and 8. So if we want to represent 2, we simply put 1 to the second bit, which means the position value is 2. Let's consider number 9. So the fourth bit, if we put 1, it means we take 8. 8 plus 1 is 9. A is representing 10, which means 8 plus 2 is A. And the D is, as you can see, D stands for number 13. So we have to make 13 here using these 4 binary digits. So this is 1, there is no 2, there is a 4, 1 and 4 equals 5, then 8. 8 plus 5 is 13, which is in hexadecimal D. And the F is 1111, which means 15. So altogether you get 15. So you can see the hexadecimal value is F. So hexadecimal to binary you can convert like this. Okay, let's consider some questions from your past papers. This is the 2015 paper, question number 10. Which of the following binary number is equivalent to the hexadecimal number of 7FF5? So you can see 4 hexadecimal digits here, which means each one of these hexadecimal digits can be represented using 4 binary digits. So here you can see the 5 is 0101, F is 1111, again F is 1111 and 7 is 0111. So when you refer the question paper there, you can see these 16 digits in the answer B. So the 2015 paper question number 10 has the correct answer in option B. Let's consider another question. This is 2014 question number 5. So what is the binary number equivalent of the hexadecimal number CBAD? Again you can see there are 4 hexadecimal digits, which means we need 16 binary digits or binary numbers to represent this number. Again you can see D is 1101, A is 1010, B is 1011 and C is 1100. Again when you refer into the question paper, you can have the correct answer in the B option and you will see these 16 bits there. Okay, now we understand how to convert decimal to binary, binary to decimal and hexadecimal to binary and binary to hexadecimal. So this is time to understand how you are going to representing numbers, especially negative numbers, how you are going to represent using binary patterns. So let's consider this. So you can see there are different ways of representing numbers. First one is unsigned representation, which is non-negative integers, which means we can represent positive integers without any sign. But still you know there are negative numbers there. So in integers we consider both positive and negative. Therefore we can have this sign representation in the integers, which means positive and negative. At the same time you can have the floating point representation, which means fractions. So today in this lesson we are going to revise first two, which means the integers and non-negative integers. So using unsigned binary to represent numbers. So like here, as we discussed up to now, we can represent numbers, only positive numbers can be represented without any sign, which means positive or negative. As you can see, when we use 8 bits, we can put all zeros or all ones. If we put all zeros, the binary sum is 0, the decimal value is 0. If we put all ones, the sum of all these position value is 255. Therefore, the decimal range is 0 to 255, but still we can have 256 separate numbers including 0. So, this is the unsigned binary, but still we want to represent negative numbers. So, simply people have thought about this and come up with a simple solution, which means we assign most significant bit to show the sign whether it is positive or negative. Then we consider 0 as the positive values, 1 as the negative values, but it wasn't successful. Now I am going to show why. You can see 3 plus minus 3 or the negative 3. So in real world, when we do the math, we can see 3 plus negative 3 equals 0. But let's consider this representation with sign bit. We have positive 3 here. So we put 1 for mention this is the negative 3, and the binary sum is 3. So which means this is the negative 3. But still when we add this positive 3 with negative 3, we will end up with the negative 6, which is not the correct answer. So here you can see binary addition. I think it is really familiar to you. Let me explain it for you now. 1, 1, which means 1 plus 1 is 0. As you know, we cannot put 2 there. We put 0 and carry 1 here. And 1, 1, the carried 1 means 3. So we cannot put 3 here. We put remaining 1 and take 2 as 1 to here. And 1, 1, 0, others are 0, and 1 and 0 is 1. But still we get the answer is minus 6. So this is not the answer that we want, which means this representation doesn't solve the problem. People thought about, no, now we have to have some other way to do this thing. So again you can see the same thing that they have done, but still they do not get the correct answer. So this should be minus 6. So then they convert these negative positions into 1's complement. This is important. Then you can see what they do is they write the positive value, and to get the negative value of that particular number, you flip all the bits. Here you can see the example. If you want minus 3, first you have to write the positive 3. 2 plus 1 is 3. And you flip all the binaries, 1s to zeros and zeros to 1. Here people thought then this will solve the problem. 1, 1, 1, 1, 1, and this is the minus 3. But the question is still when you add these two binaries, you will end up with 1 and the zeros, which gives you minus 0 or the negative 0. You can see the sign bit is 1. So therefore, and again the 1's complement also not capable of solving that particular problem, which is represented negative. Then people found out the answer, which is 2's complement. What you have to do is, if you want to write the negative of a particular number, first you have to take the positive value and take it to binary. Then you can do the 1's complement thing, which is flipping all the digits, and then you have to add 1. So you can see this is the minus 3. So this is the 1's complement. When you add 1, 0 and others remaining 1s. So here if we sum these two numbers, 3 and negative 3, then you will end up with all zeros, which is 0. So as you can see, the 2's complement solving the problem of representing negative numbers. But make sure, this is really important, if you are going to represent positive numbers, you do not want to convert into 1's complement and add 1, because positive numbers stores in computers as it is. But if you want to represent negative numbers, you have to do 2's complement thing. Otherwise, you won't get the correct answers when you are doing addition, subtraction, multiplication and division in binary format. So let's consider the 2's complement, some examples. So represent minus 76. As you can see, first you have to do is you have to write the positive 76, then do the 1's complement and then add 1. Now you can see this is positive 76, you do 1's complement, add 1, then you can see the answer is minus 76. So this is the representation of minus 76. Again you can see this is the positive 76 and minus 76. And there is another example, positive 120. So first you have to represent in positive, then do the 1's complement, then add 1. Then you will end up with minus 120. Okay, let's consider some easy way to get this 2's complement rather than doing 1's complement and add 1. Are there any easy way to do this? There is. What you have to do is write the positive of the required negative and repeat the same from right to left until you get the first one. Be careful with that, until you get the first one. Then you have to repeat up to that, then flip the rest and other binaries and you will get the 2's complement. For an example, here you can see in plus 76, 0, 0 and 1 until first one. In the negative form, the pattern is repeating. And here plus 120, again 0, 0, 0, 1, the same pattern is here. And then you can see all the other bits are flipped, ones into zeros, zeros into ones. Same thing happens here, ones into zeros and zeros into ones. So this way you can quickly get the 2's complement. It is quite easy to do so. So this is important, some questions you may get with the 2's complement range. It is really important to understand when you have 8 bits. 8 bits, your positive range is 2 to the power 8 minus 1 minus 1. But when you consider you have allocated 1 bit for the sign bit. So therefore you cannot have 2 to the power 8. So you have only 2 to the power 7 minus 1 minus 1. So why is this minus 1 is here? Because we consider 0 here as a positive value, still you can represent 2 to the power 7 minus 1. So it is simple math. You had 8 bits, then you have allocated 1 bit for the sign bit, then 8 minus 1 is 2 to the power 7 and here minus 1, which means you have to allocate 1 representation for the 0. But when it's come to negative range, you can see there is no minus 1 because 0 is gone for the positive section. Then you can start with minus 1. So you can see the smallest and the largest negative values are here, the minus 1 and minus 127. There is an exception which is minus 128. So if we consider the 2's complement with 8 bits, in other words with 1 byte, the positive range is, the maximum number is positive 127. The negative number is minus 128. So likewise you can come up with the range. So based on these lessons or the facts that you have learned up to now, let's consider some questions. So this is the 2015 question number 5. What is the 16-bit 2's complement binary number equivalent of the decimal number minus 1075? So you know the way and you can do it. First you have to write 1075. So you can see the binary values here 1, 2, 4 up to 1024. When you have 16 bits, you have no issue that you have 16 long bit to represent this thing. So you for make 1075 you can allocate 1024, 132, 116, 12 and 1 1. So from here to here you can see like this, but we need 16 bits, therefore we have to put 5 zeros to the front. Now we have 16 bits here which represent positive 1075, and you have to do the 2's complement. What you have to do is from right to left repeat the pattern until you get the first one. Here in this case you will get the first one at the very first bit, so you repeating that one, then you convert or flip all the other bits ones into zeros and zeros into 1, and you will get this answer, and you can find this answer in your question paper in the option B. And this is another question from 2015, question number 6. So you are asked to come up with the range. Which of the following is the range of integers that can be represented using 2's complement notation on a 16-bit register? Here you can see, as I mentioned, this is the negative part and this is the positive part. As I mentioned, in the positive you always get -1 because you have to allocate one representation for the 0, and but negative you can get all the representation for the negative part. Therefore in a 16-bit register you can have in the minus range -2 to the power 16 minus 1 to positive 2 to the power 16 minus 1 minus 1. So the answer is option B. And there is another question. This is 2014 question number 7. So you can see the number 0 and 15 ones in the forms of 2's complement is equivalent to decimal number. This question is little bit tricky. You might think if this is in 2's complement you have to flip the binary and do the calculation, but it is not, because you can see the sign bit is 0, which means this is a positive number. Positive number, it is stored in the computer as it is, which means you can simply add all the position values here and take the final answer. But this kind of addition might be little bit difficult. Therefore it is better if you can remember your lessons from the classroom, which means you know if you have 16 bits, the 16 bit value is 32,768, but then you can see there is all ones here, which means the addition of these numbers gives you 1 minus to the this position value, which gives you 32,767. So the answer is D. So there is another question, and again you can see the same question asked in 2015 question number 7. They are asking about positive 32,767, which means you do not want to do the 2's complement or 1's complement because this is a positive number. You can simply say, okay, this is the correct answer, option C. Okay, it's about the revision 1, the arithmetic about binary, decimal to binary, binary to decimal, hexadecimal to binary, binary to hexadecimal, and 2's complement. So hope you get the idea and prepare for your exam well. Thank you.